Talking about ratios and proportion, what a ratio is and what a proportion is. The most common ratio example that you've probably dealt with before is the ratio of maybe boys to girls in a classroom, which looks like in here, probably, let's say the ratio is 21 to 7. There's three different ways that ratios could be written. Sometimes they're written as fractions, okay? Sometimes they're written as with a colon, and sometimes they're written with the word 2, 21 to 7. But actually, all three of them are read as 21 to 7. A ratio is a comparison. And here's the thing, 21 to 7, now that tells us exactly, and let's go with that. Let's just, I know that's a little bit off. That's actually way off. But let's go with that, that's exactly, there's exactly 21 girls and exactly 7 boys. Let's say that is a true statement. The same way that a fraction can be reduced, a ratio can be reduced. 21 to 7, somebody reduce that ratio for me. What does it reduce to? 3 and 1, right? And a lot of times when you're dealing with ratios, they'll go ahead and still put that 1. Because again, you're comparing boys with girls. So 21 to 7 reduced to 3 to 1, 3 to 1, or 3 to 1. So not always will a ratio tell us exactly how many boys and how many girls. It compares them. Like 3 to 1, does that tell us there's exactly 4 people in here and there's 3 girls and 1? No. It tells us for every 3 girls there is a single boy. Or maybe for every 4 boys there's a single, or there's 5 girls. Or for every 3 girls there's 6. You know, it doesn't necessarily tell us exactly how many. That's what I want to get across. It doesn't necessarily tell us exactly how many there are, but it compares them. For every 3 boys, there's 4 girls. For every 4 girls, there's 5 boys, okay? 2 ratios, such as 21 over 7 and 3 over 1. 2 ratios that are the same are called proportions. Proportions are simply equal ratios. 4 to 8, 3 to 6 are proportions, okay? Show you a trick on this, and you've probably seen it. Like I said, 3 to 6 and 4 to 8 are equal ratios. They form a proportion. A proportion is simply 2 ratios that are equal. Anytime you have equal ratios, again, this one's free. Won't cost you anything. Cross product should always be equal. Anytime 2 ratios, and that gives you a trick. Anytime you're dealing with fractions and somebody asks you, hey, I need to know, is 5/7 the same thing as 7/10? What's an easy way to see it? Because again, ratios, fractions, pretty much the same thing. If you want to see if 2 ratios are the same, see if the cross products are the same. Because look up here, these were the same, right? 24, 24, cross products are the same. Is 5/7 the same thing as 7/10? But how close is it? It's very close, right? 5/7 is basically the same thing as 7/10. It's nearly the same thing, but it's not exactly the same. Because look at your cross products. 5 and 10. What does 5 and 10 give me? 50. What's 7 and 7 give me? That's close. 5/7 and 7/10 are nearly identical fractions, but they're not. They're just a little bit off. Okay? So anytime you're dealing with proportions, that's one way to test to see if you have a proportion. In triangle ABC, let's find ABC. Here it is. In triangle ABC, what is the ratio of side lengths AB to side BC? And this is just giving you some practice with proportions and some ways that you might see proportions written. In triangle ABC, let's see, what is side length AB? Can anybody see it from back there? What's side length AB? 5, good. The distance from here to here is 5. What's side length BC? BC is 4. So the ratio of AB to BC would be 5 to 4, 5 to 4, or 5 to 4. Any way you want to write it. Those will not reduce, so we just leave it as 5 to 4. It says here, what is the ratio of the area of the rectangle to its perimeter? We're going to talk more about area and perimeter later. I was just saying how much you remembered from 7th and 8th grade math, what area and perimeter was. What is the relationship between area and perimeter? Anybody, and like I said, this is not what we're doing in this chapter. I'm just saying how much you actually remember. What is one reason, some of y'all that might have actually dealt with it in real life, what's some scenario in real life that you might need to use area? Does anybody know? When do you use area? Does anybody know what area is? Look down, you see it. You see those tiles? How big is those tiles? It's 1 foot square. That is a square foot. Why is that tile a square foot? Because it's 1 foot by 1 foot. That is what a square foot looks like. It's a 1 foot by 1 foot square. So why would we need to use area? Well, one reason is to see how many tiles it would take to cover this floor, right? Well, if we know our room is 50 foot by 20 foot, well, could we not just say, well, we're going to need 20 rows of 50? Does that make sense? Because you need 50 20 times. So to find out what the area of the room is, if it's a rectangle, it's pretty easy. You just multiply with how long it is by how wide it is. 50 by 20, if that was a true scenario, 50 by 20, that would mean it would take 1,000 tiles to cover the floor. It's pretty close. The area of this. It's an 8 centimeter by 4 centimeter rectangle. Does anybody know what the area is? 32. So one scenario that you need area is coverage. Anytime you see the word cover, how many tiles would it take to cover the floor? How much carpet does it take to cover the floor? How many paint does it take to cover the wall? Anytime you're talking about coverage, you're talking about area, but that's a chapter later today. Perimeter. Okay, now a completely different concept. When do we need to know perimeter? There you go, baseboard. If you need to know how much baseboard it would take to go around the room. Perimeter, here's what I think about when I see the word perimeter. Rim. You're talking about the rim of something. The distance around it. And that's what perimeter is. How far is it around this room? How far is it around this rectangle? Well, the distance is 4 from here to here, 8 from here to here, 4 from here to here, 8 from here to here. Somebody know what the perimeter of that is? 24. So therefore, the ratio of the area to the perimeter would be, and I'm not really concerned about units, but if you wanted to, it's 32 square centimeters to 24 centimeters. We'll just worry about the 32 and 24 for now. But we don't leave it like that. We always reduce if possible. We find some number that will divide into both. 8 will divide into both, so we divide top and bottom by 8, and it gives me 4 to 3. There's your ratio. And you can write it any of the 3 ways. Which means for every 4 square centimeters that we have of area, we have 3 centimeters of perimeter. Okay. Next problem, let's talk a little bit about ratios. And this is what's called an extended ratio. It's not like boys to girls anymore. It says the ratio of the measures of the side lengths of a quadrilateral. Does anybody know what a quadrilateral is? I know we haven't done quadrilaterals, getting a little ahead of ourselves, but you've done them in the past. What's quadrilaterals? Anybody know? Quad. What's the prefix quad mean? 4. So a quadrilateral has 4 wheels. Quadrilateral is something with 4 sides. So you have this 4-sided shape, such as rectangle, square, those are all quadrilaterals. You have this 4-sided shape, and its side lengths are in ratio 2 to 3 to 5 to 4. That's an extended ratio. You don't have a ratio of boys to girls. You have a ratio of this side to this side to this side to this side. So it's a little bit longer ratio, but that's fine. Now, the question I'm about to ask you, I will ask you multiple times this year, so get used to it. Is 2, 3, 5, and 4 the side lengths of that quadrilateral? The ratio, let's say the ratio, what was it, like 3 to 1 or something like that is what we did a while ago? Yeah. The ratio of boys to girls in here are 3 to 1, let's say. Does that mean there's 3 boys and 1 girl? No. Does this mean the side lengths of this quadrilateral are 2, 3, 5, and 4? No. But let's talk about what the side lengths could be. Could that be 2, 3, 5, and 4? Yes. Because what that would have meant was, well, the side lengths didn't reduce, that's them. But if you add those together, I get 14. So what y'all get? It says here the perimeter is 154, not 14. That's not the side lengths. The side lengths could be, let's talk about all the things it could be. It could be 4, 6, 10, and 8. Now, where in the world did I get that? Doesn't 4, 6, 10, and 8 reduce to 2, 3, 5, and 4? Yes. Now, add those together, 10, 28. No, perimeter is supposed to be 154. Distance around is 154. That's still not it. The side lengths could be, I could take all this and I could multiply by 3. And I could get 6, 9, 15, and 12. Now, that reduces to 2, 3, 5, and 4. But that's still not it. I'm doing this the hard way. What I'm trying to get at is the side lengths, since it reduces to 2, 3, 5, and 4, the side lengths of this quadrilateral has to be some multiple of 2, 3, 5, and 4. Now, let me explain what I mean by multiple. What are some multiples of 3? 3, 6, 9, 12, 15. How do you find multiples? You take the number 3 and you, one word, multiply by something to get, okay, to get those other multiples. So I know that since my ratio is 2 to 3 to 5 to 4, that my side lengths are going to be some multiples of 2, 3, 5, and 4. Like I could multiply all these by 2, I could multiply all these by 3, I could multiply all these by 4, and that would give me some ratio that reduces to this. But I don't know what number to multiply by. So I know my side lengths are 2 times something, 3 times that same something, 5 times that same something, and 4 times that same something. Those are the side lengths. But I don't know what the something is. But I do know something else about my quadrilateral. It says the perimeter is 154. Go back to what we just did. How do you find perimeter? We had a rectangle a while ago, and we found the perimeter of it. How do we find the perimeter? Perimeter is the distance around it, right? So how do you find perimeter? You add the sides. So there's my sides. 2x, 3x, 5x, and 4x, is that not my 4 sides? I know that when I add those sides together, I will get the perimeter. What is that? A linear equation. That's the reason that we were solving linear equations last night. Now that's a little bit easier than the ones that you solved. I know that when I add my 4 sides together, I will get 154, which is the perimeter. We set up the equation, we're going to solve it, and hey look, all my x's are already on the same side. 2, 3, 5, and 4 gives me 14x equals 154. Last step, divide by 14, I get x is 11. That is not the side lengths. That pretty much is what you're going to multiply to get the side lengths. My side lengths were 2x, 3x, 5x, and 4x. So, Jordan, other one. Since x is 11, instead of having a side of 2x, I now have a side of 2 times 11. Jordan, what is 2 times 11? 22. So I have a side length of 22. What's this side length, Jordan? 3 times 11? 32. And? 55. And? 44. Those are the 4 sides. Now let's check it. And you don't have to check all these, but I want to show you how you could check it. Number 1, it said that my side lengths are in ratio of 2 to 3 to 5 to 4. If you took these 4 side lengths and reduced that ratio, well, number 1, how would you reduce it? What would you divide by? Think about it. How about 11? Take all these 4 side lengths, reduce the ratio. Here's the 4 side lengths, set them up in ratio of each other, reduce it by 11, you get 2, 3, 5, 4. So are those in ratio of 2, 3, 5, 4? Yes. Number 2, we need a perimeter of 154. 22 plus 33 is 55. 55 plus 55 is 110. 110 plus 44 gives you 154. Okay, checks out. Let's work another one. The ratio of the measure of the 3 sides. Okay, a little bit easier now. The 3 sides of a triangle are 9 to 7 to 5. So are those the three sides of my triangle? It says the perimeter is 191.1. If this was the three sides of your triangle, would it have a perimeter of 191.1? No. So that's the ratio of the three sides. That's the comparison. I know that this side is the longest, and this one's a little shorter, and this is a little shorter. That's pretty much what they told you. But Megan, see if that last problem made sense to you. Megan, 9, 7, and 5 are not the side lengths, but how could I represent the side lengths? Even though they're not 9, 7, and 5, I could represent them with 9. What? 9. How about 9x? Megan, and those are the three sides. That makes sense. I know that my three sides are some multiples of 9, 7, and 5. It could be 18, 14, and 10. It could be 27, 21, and 15. Some multiple. And that's how you write some multiple. 9 times something, 7 times something, 5 times something. And I know the perimeter. I know the perimeter is 191.1. So, Erica, how could I use these three sides to find the perimeter? What do you do to find perimeter, Erica? You add the sides. So I know when I add the sides, I'm going to get the perimeter. 191.1. That's how you set up these problems. Makes sense. The ratio of the three sides is going to give you pretty much a representation of the three sides. The perimeter is what you're going to get when you add them up. When you add them up, you will get 191.1. We solve it. I get 21x equals 191.1. To get rid of 21, we will divide by 21, and I get x is 9 point something. Is it 9.1? Huh? 9 point what? Should be 9 point something. It is 9.1. So here we go. X is 9.1, and what that does for you is your three side lengths are 9x, 7x, and 5x. Since x is 9.1, this side length is no longer 9x. It is now 9 times 9.1, or 81.9. The middle side length is no longer 7x, but now 7 times 9.1, which is 63.7. And your last side length is no longer 5x, but now 5 times 9.1, which is 45.5. If you reduce that ratio, and that's an ugly ratio, isn't it? 81.9 to 63.7 to 45.5. But you know what? You know what to reduce by. If you divided all three of those by 9.1, you would get 9, 7, and 5. And not only that, if you add all three of those together, you should get a perimeter of 191.1. Okay. Next piece of review we're going to do is involving graph. Square roots. A square root and a radical is the same thing. To find a square root of something, which, by the way, are there other types of roots? Sure. There's square roots. There's what's called cube roots, fourth roots, fifth roots, sixth roots, seventh roots, 10th roots, 20th roots, 100th roots. There's all sorts of roots. The only ones you've ever dealt with was square roots. When you get into Algebra 2, pre-calculus, you'll deal with third roots and fourth roots and all these other roots. A square root is simply what do I multiply times itself. There's two numbers there. What am I going to multiply times itself in order to give me this number? Such as the square root of 64. What number can I multiply times itself to give me 64? You get 8. Square root of 4. What number, Sierra, do you multiply times itself to give you 4? And what's special about the square root of 4? It is the only square root that you can get not only by multiplying times itself, but also adding to itself. Just lied to you. There's two of those. There's only two square roots that not only is that the same number that multiplies times itself, but it also adds plus itself and gives you that same. Because 2 times 2 and 2 plus 2 both give you 4. What's the other ones? There's one other square root that you can get by either multiplying times itself or adding to itself. Square root of 1. Let's try 1. Square root of 1 is 1. But if you did 1 plus 1, you get 2. Square root 30. You talking about square root of 6? You're thinking 2. I see what you're doing there. How about 0? Yeah, that's the only other one. Square root of 0 is 0. You can get that by either multiplying or adding. So that's the only 2. Square root of 121, somebody know that one? 11. Square root of 1. That's the one people miss. People put a half. What times itself, not what plus itself, what times itself. That's the reason I said that a while ago. Square root of 100 is 10, square root of 49 is 7, square root of 16, 4. Make sure, sometime between now and tomorrow, what I would do, set and make a list of all your perfect square roots. Square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, square root of 16 is 4, square root of 25 is 5, square root of 36 is 6. Make a list of maybe the first 15 of them, because you might need them for what we're about to start. What about the other ones? Square root of 18, another one right off the top of your head. Square root of 18, well, the square root of 16 is 4, square root of 25 is 5, so the square root of 18 is somewhere between 4 and 5. Which is it closer to? Square root of 16 is 4, square root of 25 is 5. Wouldn't that be closer to 4? Because 18 is closer to 16? Square root of 63, that's really close to what? Square root of 64, which is what? 8. So do you see the square root of 63? Well, that'd be a little bit less than 8. The square root of 72, well, that's somewhere between 8 and 9. Because the square root of 64 is 8, the square root of 81 is 9. That's nearly right there in the middle of 8 and 9. That's about 8 and a half. But what about these? Let's talk about exact versus approximate. If you type the square root of 18 into your calculator, because we need to know what multiplies times itself to give me 18. You get 4 point, somebody type it, and give me 3 decimal places. 2, 4, 2 for what? 2, and then what does it round up? So it's 4.242. Dot, dot, dot. Let me explain something about that. That's not exact. What if I wrote down every number on my calculator screen, then is it exact? No. The square root of 18 is what's called an irrational number. Anybody ever heard that word irrational? You know about pi? If you evaluate pi, 3.14159, when does it stop? Never. Does it repeat? You might have the same number thrown in there, but is there any pattern? No. It's been calculated to millions of decimal places, and there's absolutely no pattern. That's an irrational number. So my question for you is, the square root of 18, if it's irrational, let's say that you're building a bridge, and I use this example a ton. You're building a bridge, and you do this calculation, and it comes out to be the square root of 18, and you know what you do? You take that and you chop it off at 4.242, and you say, okay, the square root of 18 is this, and then you use that number to find another answer. And then you use that answer to find another answer, and that answer to find another answer. You know what you just did? Each time you use that number, again and again and again, your actual answer is a little bit further off, because this is not exact. This is exact. Okay? This is a rounded answer. And anytime you use a rounded answer to find another answer, you ever done that thing where a big group of people sit around in a circle and you whisper something in one person's ear, and by the time, you know what I'm talking about, by the time it makes it all the way around, it's a little bit further off. Math is the same way. If you use a rounded answer to find another answer and another answer and another answer, your final answer will be not near as close as it should be. So if you're building a bridge, and you might have seen the video or the picture before, where and usually when you look at the bridge in Scottsboro, how do they build it? A lot of times they'll start on one side, start on the other side, and meet in the middle. Well, guess what? If you use rounded answers, you're not going to meet in the middle. It might be a little bit off. So let's talk about exact versus approximate. If at all possible, don't use approximate. Use exact. And these three values here are exact. Square root of 63, that was like 7.89, somewhere around there. But that's approximate. Square root of 72, that's somewhere between 8 and 9. It's 8.4, 8.5, but that's approximate, okay? So let's talk about how you find exact, or what you can do with exact. The same way, everybody knows how to reduce fractions, and we'll do this and then we're finished for the day. 3 over 6. I hope that bothers you to see 3 over 6 now. I hope that's just, it's a pet peeve of yours now that if you see 3 over 6, you just have to reduce that. That just don't look right. 3 over 6 reduces. We divide the top bottom by 3, we get a 1, we get a 2. We're done. Okay, we're good with that. The same way that we reduce fractions, we can also reduce radicals. The same way that you reduce fractions, radicals can also be reduced. And you might remember these from algebra. Hopefully you did some in algebra 1. Here's how you reduce radicals. Let me show you something pretty cool. Square root of 4 times square root of 9. What is the square root of 4? What's the square root of 9? So that's 2 times 3, right? What is 2 times 3? Can you multiply square roots? 2 times 3 is 6, right? Isn't that what you tell me? Does that say 2 times 3 equals 6? Sure. What's the square root of 36? Where did I get 36? 4 times 9. Let's try that again. The square root of 16 times the square root of 4. What's the square root of 16? 4. What's the square root of 4? So that's 4 times 2, right? What is 16 times 4? Somebody type that in. What is 16 times 4? 64. Is that true? 4 times 2 equals 8. Can you multiply square roots? Yes, you can. Since we can multiply them, we can also factor them. Remember factor trees? 72 breaks down into 8 times 9, breaks down into 2 times. Y'all remember factor trees? The same way that you can break apart 72, we're going to break apart these things as well. So keep in mind what I just said. You can multiply square roots, and since you can multiply them, I can break them apart. Square root of 18. Here's how you reduce a radical. First step, break it into something that you do know the square root of. I have no idea what the square root of 18 is. Now, I do know the square root of 4. I know the square root of 9. I know the square root of 16. I know the square root of 25. I know the square root of 36. Let's break 18 apart. Somebody give me something that multiplies to me 18 that's not a perfect square. How about 3 times 6? Everybody understand 3 times 6 is 18? Does anybody know the square root of 6? Was that on my list? Does anybody know the square root of 3? No. What else multiplies to give you 18? 2 and 9. So can I split the square root of 18 into the square root of 9 times the square root of 2? Yes. Because what is the square root of 9 times the square root of 2? Square root of 18. Now what can I do with that? What was my list again? I know the square root of 4. I know the square root of 9. I know the square root of 16. I know the square root of 25. What is the square root of 9? Good. Mark that out. Put. You just reduced it. How did I reduce it? I got as much out of the radical as I could. I pulled some of that 18 out of a radical, and I put it on the outside as a whole number. The square root of 9 is 3, so I turned the square root of 9 into 3, and I left the square root of 2. Why did I leave the square root of 2? Because I don't know the square root of 2. That makes sense? Now let's test ourselves. You reduced it. We're good. We actually reduced it all the way because 2 won't break down any further. You ever done this? You ever had 10 over 20? You divided it by 5 and got 4 over, excuse me, let's try that again. Divided it by 5 and you got 2 over 4, and you circled it and the teacher still marked it wrong and got frustrated, right? You reduced it, but you didn't reduce it all the way. Okay, so we got to be careful about that in a second. We've got to make sure that we're reducing these all the way. But before we do that, let's check this. So the square root of 18, I'm saying is the same thing. Anytime I write these next to each other, that's 3 times the square root of 2. Keep that in mind. And a lot of times I'll read this as 3 root 2. Oh, that's how I say it. 3 root 2. Somebody type, tell you what, left side of the room, if you got a calculator, type in the square root of 18. Right side of the room, and in the middle, you're going to do either one. Right side of the room, type in 3 times the square root of 2. Jackie, did you type one of them? Which one did you type in? 3 root 2?
Yeah.
What'd you get?
I got 4.2.
4.2? And somebody on the left side of the room, square root of 18, what'd you get? 4.2. Is that the same thing? Yeah. So the square root of 18 and 3 times the square root of 2 is the same thing. This 3 times the square root of 2 is reduced. Let's do another one. Square root of 63. Go through the whole list of things that multiply to give you 63, but you need something that you know the square root of. 63. What multiplies to give you 63? Square root of. Somebody know 63? 7 and 9. And I do this. I always do put the one first. I know the square root. Square root of 63 is the square root of 9 times the square root of 7. Hey, I know the square root of 9. What is the square root of 9? So 3 root 7. And there's understood to be a dot there. That's 3 times the square root of 7. Done. It's reduced. Pull out from under the radical as much as you can. This is no longer under the radical. Now it's a whole number. 3 times the square root of 7. You can check it by multiplying both of them together. 3 times the square root of 7 should give you the same. It's like 7.9 or something like that. Yeah, somewhere around in there. The last one. And which, by the way, take the square root of 7. Will anything else multiply to give you 7? Just 1 and 7, right? Do we know the square root of 1? Yeah, but that's not going to help you very much. So we're good there. The last one. Now I'm going to work this one the easy way and the hard way. Of course, we do the hard way first just because that's what math teachers do. I always like to do things the hard way and then show you the shortcut. Square root of 72. Break that into the square root of 9 times the square root of what? 9 times 8. Clean that up for me, Brianna. What is the square root of 9? So that'd be 3 times the square root of 8. And a lot of you circle it, and that's just like that teacher that marked off for reducing 10/20ths to, what I reduce it to, 10/20ths to 5 or 2/4. Yeah, they mark off for that too. 3 times, but is that right? Yeah, but it's not reduced all the way. Look at the square root of 8. This is 3 times the square root of 8. What can you break 8 into? 4 times 2. You know the square root of 2? No, but you do know the square root of 4. So you could have actually reduced that again. So let's leave the 3, and let's break the square root of 8 into the square root of 4 times the square root of 2. Reduce it as many times as you can. And the reason I was able to do that again is, hey, I know the square root of 4. Rachel, what is the square root of 4? So I can mark it out, and I can put 2 there. So I now have 3 times 2 times the square root of 2, or I can put those together. 3 times 2 is 6 root 2. Root 2 will not reduce any further. You're done. Another statement I will make a million times this semester. The reason I can multiply 3 and 2 together, those are both whole numbers. You can multiply whole numbers with whole numbers. You can multiply square roots with square roots, but you cannot multiply a whole number. 3 times the square root of 8 is not the square root of 24. You can multiply roots with roots. You can multiply numbers with numbers, but you cannot multiply numbers with roots. Remember that. So now that we've done that the hard way, somebody share with me, what was the easy way to have done this? Does anybody know? 6 root 2 is the answer. Is there a different way you could split 72? Think about your answer. Why did we not split it into the square root of 36 and the square root of 2? Would that have been easier? Is 36 times 2 also 72? Yep. If I would have split it into the square root of 36 times the square root of 2, well, what is the square root of 36? 6. So then you went straight to your answer. So lesson learned. when you're simplifying radicals, use the biggest number possible that you know the square root of, because if you use too small of a number, you might have multiple steps in it.